Welcome to Wallah one-shot series. This is 𝐂𝐨𝐻𝐿𝐴, Faculty of Measurements and Instrumentation. So, as a consecutively, we are discussing in the measurements all the topics in one shot. And now, today's lecture, we are going to discuss about the Q meter in one shot. We are going to cover Q meter in one shot. So, let us see what is the agenda of today. I am going to discuss the working of the Q meter, the applications of the Q meter, and some numerical problems related to Q meter. So now, first of all, what is a Q meter? Before understanding Q meter, you should know what is a Q factor. The quality factor of a coil, which determines the energy storage capability. The energy storage capability of the coil is determined by a figure of merit called Q factor. It is one property of the coils. So to measure this, we are using one instrument. The instrument name is Q meter. Along with the Q factor, we can also measure certain other parameters like self-inductance of the coil, distributed capacitance of the coil, resonant frequency of that particular circuit. So these all measurements we can do by using the Q meter. So before entering the instrument, you can see the text. The instrument which measures the storage factor or quality factor of the electrical circuit at radio frequencies, such type of device is known as the Q meter. Works at the radio frequencies. The quality factor is one of the parameters of the oscillatory system which shows the relation between the storage and dissipated energy. As you are aware, for a Q factor is defined actually as omega L by R, but how this relation came? This is based upon the relation of energy dissipated by energy storage. Okay, so this is the dissipated, this is the storage. Okay, so if you take this omega L, I gets cancelled and this is the R. So this is the way how we got the expression for the Q factor. Q factor is defined as quality factor of the coil. Okay, now if you see, to understand the Q factor, you have to go for the resonant circuit. I think all of you are aware of the resonant circuit. I don't want to discuss much about the resonant circuit because the resonant circuit is available for you in network theory. It is a RLC circuit. So at resonance in this circuit, what happens? The inductive reactance and the capacitive reactance both are going to be equal and opposite. Then that particular circuit becomes pure resistive type circuit. So at the resonance, XL and XC, that means both are XL minus XC. If you take, they are going to be 0. That means XL is equal to XC. This XL and XC, that means this is the inductive reactance. Suppose if you see this a voltage across this resistor, this is a VR, and this voltage across this inductor we can say I into XL, and the voltage across this capacitor we can take I into. Okay, so this one I can take it as I into R. So now what happens? The circuit becomes like a pure resistive circuit. For a pure resistive circuit, the voltage and the current both are going to be in phase equal to each other. Okay, they are going to be in phase to each. Whereas for an inductive circuit, the voltage and current, okay, the voltage will be leading. Okay, now for a capacitor, the voltage will be lagging. But when it comes to the resistive circuit, the voltage and the current both are going to be in phase to each other. So if you see the net impedance of this particular circuit, the net impedance is equal to R. It is going to become at resonant frequency. It is not going to happen at all the situations. At a particular frequency called resonant frequency. At resonant frequency, so this particular total impedance of the circuit going to become resistive circuit. Why? Because the XL and XC are going to be cancelled. Okay, dear. So as I mentioned, since at resonance the opposition to the flow of current is only due to the resistance of the circuit, at this condition the circuit draws maximum current. So when it draws the maximum current, we are going to get the maximum amount of the voltage which is equal to the supply voltage. So that is what is going to happen in the resonant circuit. So if you see this particular circuit, XL and XC. So if you see XL means omega L that means 2 pi fl. So as the frequency is increasing, the XL also increases like this. So this is the way XL is increasing. Next, if you see the XC, 1 by omega c, that is 1 by 2 pi fc. So as the frequency is increasing, the XC is going to decrease inversely. So this is what going to happen. Okay, as the frequency is increasing, X is decreasing. So as the frequency is increasing, this is decreasing. As the frequency is, this is the capacitive reactance, my dear. So try to understand the capacitive reactance and cell. Okay, so at a particular frequency called resonant frequency, what happens is XL and XC are going to cross each other. So this particular frequency, we call it as XL is equal to, at XL is equal to XC, which is called the resonant frequency. At resonant frequency, the inductive reactance and capacitive reactance both are going to be equal to each other. At that particular moment, the circuit becomes like a pure resistive circuit, my dear. So now, if you see the phasor diagram at a resonance, so these are our basics that already you have studied in the RLC circuits or network theory or circuit theory. So if you see this phasor diagram, so this is a phasor diagram. So if you see this is a current. Okay, so if we take the voltage phasor diagram for the inductor, the voltage across the inductor, if you see the voltage across the inductor, so this is the voltage across the, so this is what we call voltage. Actually, purely speaking, what I say 90 degrees, okay? But practically speaking, what happens, it is going to come from phase angle. And next, XC, that is going to be opposite direction like this. Thus, for the capacitive, for the inductive circuit, voltage leads the current. For the capacitive circuit, voltage lags the current. So now if you take practically, it's not exactly like this. So now these are, both are, if you are observing, both are going to be same, parallel to each other. See, try to understand, my dear. What I want to say, ideal circuit is a pure inductive circuit, the voltage leads the current. If it's a pure capacitive circuit, the current leads the voltage. If it's a pure inductive circuit, voltage leads the current. The pure capacitive circuit, current leads the voltage. But practically, no inductor is pure. It may be having some resistance component also. So that's why the vector comes here. And similarly, 90 degrees is not possible. It comes like this. So now these two are resultant, coming like this. So these two are going to be each other equal, and this is the resistive component. So there is a voltage drop across the resistor will be phase with the current. So that's what I mentioned. The voltage across a capacitor is expressed as I into XC, which is equal to I into XL, because XC and XL both are going to be same. XL is equal to omega L. So now if I am taking here, most important point I want to tell you, how to find out the Q factor of that particular meter or particular circuit. Okay, a particular circuit. So if you take the ratio of voltage across a capacitor to the voltage of the supply, because at resonance what happens? At resonance, this output voltage is going to become as what? R into I. Proven. At resonant, the output voltage is equal to supply voltage, which is a pure resistive circuit, R into I naught. So if you take the ratio of these two, I am going to get omega L bar, which is nothing. That means at resonance, the voltage across the capacitor will be Q times of the supply voltage. So please try to understand this logic. At resonance, the voltage across the capacitor is equal to Q times of the voltage. So based on this, we are going to get the instrument. So this is what we call circuit of the Q meter. So if you see the circuit of Q meter, the first part that we are going to measure is the measurement of Q. That is what quality factor. First, I want to explain the circuit. The circuit contains, first of all, like oscillator. From this oscillator, we are going to generate the resonant frequency. We are going to adjust this particular circuit to operate at a radio frequency, and that frequency is going to be called as resonant frequency ladder. And we are going to take the test coil here. So, for test coil, what are the parameters that a coil can contain? The coil will be having some self-inductance. The coil will be having some distributed capacitance. Yes, you may be having a doubt, sir, how it is possible for a coil a capacitance? If you see, when a current is passing through that particular coil turns, there is a possibility of positive and negative charge because of the directional change of the current when it is moving into the turns. When the current is moving through the turns, there is a possibility of positive and negative charge, which is called as some distributed capacitance. Or in a simple words, if you want to say, no resistor is a purely resistor, it may be having some inductance capacitance effect. No capacitance is a purely capacitor, it may be having some inductance resistance effect. Vice versa. Similarly, inductance is also not a pure inductor, it may be having some resistance and capacitance effect. Okay, so now if you see the distributed capacitance, so these are distributed capacitance. So this parameter also we have. Okay, and we are keeping a shunt resistance here. Why the shunt resistance? Because we want to know the voltage that we are taking. So that voltage across the shunt, but measured by voltmeter. The voltmeter name is thermocouple volt. In this circuit, there are two types of voltmeter. One voltmeter is near to this resistor, so which we call it as thermocouple voltmeter, and another voltmeter we have kept at the back end capacitor. Two capacitors are there. One is a constant capacitor. Remember, the coil is having one constant capacitor. Okay, the coil is having one constant capacitor. Excuse me. The coil is having one distributed capacitance which is constant. Okay, the coil is having distributed capacitance, and this is the tuning capacitor. By adjusting this tuning capacitor, we are going to make the circuit to operate at a resonant. I don't understand. By adjusting this tuning capacitor, we are going to get resonant frequency. Sir, how to get resonant frequency? That I will tell you. What is the condition? At resonance, the voltage across the capacitor is going to equal to the supply voltage, or not? Q times of supply voltage. That is a maximum voltage. Okay, so that's what we have mentioned, right? So if you see here, output voltage is equal to Q times of the E voltage, whereas output voltage is nothing but the voltage across the capacitor. That is a maximum voltage. Okay. So we are using the electronic voltmeter, and this is our coil. Across the coil we have kept a distributed capacitance. So now when the current is traveling here, now when the current travels here, we are going to get the supply voltage. That's fine. And now what I will do, I will going on adjusting this particular capacitor. First of all, I will fix this resonant frequency at a particular point. I will be going on adjusting this capacitance such a way the voltage across this capacitor should be maximum. I will go on adjusting that capacitor such a way the voltage across this capacitor is maximum. So this voltage is called electronic voltmeter. Okay? So that is EC. Okay. So this voltage I am going to taken, and if I take the ratio of these two, that should be, thus EC is equal to Q times of E ray, just before you have seen. If you take that voltage across a capacitor and the applied voltage E is the supply, we can say, so which you are going to get from where? That you are going to get from thermocouple based voltmeter. Thermocouple based voltmeter. Next, and if you see the EC, there is a voltage across the capacitor. So this voltage across a capacitor is what? That is the maximum voltage at capacitor at resonant frequency. Call it as maximum voltage of the at the tuning capacitor at resonant frequency. So for this we are going to take electrostatic voltmeter. Electrostatic voltmeter or electronic voltmeter. So once you get these two values, take the ratio of EC by E, that is nothing but Q. Q factor we can take it as E by E. Okay, what we have proven, the voltage across the capacitor is equal to Q times of the E. What we have proven just. So this is a first measurement. See, Q meter is having many application, and this is a first measurement. And the second measurement of inductance. Measurement of inductance, how to know it? As you know, the resonant frequency R equal to 1 by 2 pi root LC. So if you make the square of it and if you take that, you are going to get from this. Okay. Next, measurement of effective resistance. Effective resistance ka formula, that is Q value is equal to omega L by R. Once you get the Q factor, you can get the R value omega L by Q. So I got the resistance of the coil, I got the resonant frequency, and I got the Q factor. And most important thing, you want to get the distributed capacitance. How to get this? So to get this distributed capacitance, I want to tell you one important point. What is a distributed capacitance? See, this is our coil, right? So this coil around, we are having distributed capacitance. So this distributed capacitance is constant, but this tuning capacitor is not constant. Tuning capacitor value goes on changing. According to at different resonant frequencies, we are going to get different. See, at different CT values, we can make the resonancy. Okay. So actually speaking, what resonant frequency formula FR is equal to 1 by 2 pi root of L. Not only this one, these two are going to be parallel to each other because this is coming here. So it is going to become distributed capacitance plus the tuning capacitance. So then how to find out this? Who is changing here? The tuning capacitance is changing, the CD is not changing. So how to get that CD value? First, make a certain value of C1 here, 1, and achieve the resonance. Understand? First fix that particular tuning capacitance, go on changing. You will achieve at a particular zone resonant frequency. How to identify resonance is achieved or not? My dear, how to identify resonance is achieved or not? At resonant, what happens? The voltage across the particular capacitor is going to become maximum. Okay na? So FR1 is equal to 1 by 2 pi root over L CD plus CT1. Next, FR2, now what you will do? Change the frequency to some 2 times or 3 times. Suppose FR1, if you are taking 500 kilohertz, choose the FR2 as 2 times of it, that means 1000 kilohertz, and you go on changing the tuning capacitance again at another value of tuning capacitance. FR2 is at another value of capacitance, you are again going to achieve the resonant frequency. So this is 1 by square root of L. Distributed capacitance will be constant. I don't understand. When resonant frequency changed, automatically the voltage across a capacitor is not going to be maximum, because you have to adjust the tuning capacitance. When you adjust the tuning capacitance and at a particular value of tuning capacitance resonant frequency only, it is going to achieve. So now if I am choosing FR2, suppose imagine it is a 2 times of FR1. You have chosen a second resonant frequency which is 2 times of the resonant frequency 1. So what I can write, this is 1 by 2 pi square root of L CD plus equal to, this is a 2 times of FR1, 1 by 2 pi square root of 2 t plus like this. Understood? అంటే ఫస్ట్ రెసొనెంట్ ఫ్రీక్వెన్సీ టూ టైమ్స్ ఆఫ్ ఫస్ట్ రెసొనెంట్ ఫ్రీక్వెన్సీ equal to the second resonant frequency. Okay, so let me finalize this. So if I cast, so 1 by L into TD plus equal to 4 by L into T plus LL get. Okay na? So I want the distributed capacitance, right? Write it 4CD plus 4C2 equal to plus. So if I want the CD plus 4C2 is equal to, so CD is equal to 1 minus 4C2 by that is the distributed capacitor, one of the important parameters. We can find out the inductance of the coil, we can find out the effective resistance of the coil, we can find out the Q factor of the coil, and we can also find out the distributed capacitor. Let us move for the next question. Now let us start the questions. So first question I want this. Now we'll see this problem. A reading of 120 is obtained when a standard inductor was connected in the circuit of a Q meter and the variable capacitor is adjusted to a value of 300 picofarad. That means what? When there is an inductor connected and there is capacitor line. Okay. So the capacitor value here was 100 picofarad. At this point, the factor E 120 is 120. Okay. Next, a lossless capacitor of unknown value Cx then connected in parallel with a variable capacitor. Now what happened? To one more unknown capacitor parallel, then this is tuned, the tuning capacitor, right? A lossless capacitor of unknown value Cx then is connected in parallel with a variable capacitor and the same reading was obtained, and the variable capacitor is readjusted to a value of 200 picofarad. This is now readjusted to 100 factories. See here, it is readjusted. You understand the value of Cx is what? Cx. So previously it was 300 picofarads. So Q factor should not change, means the total capacitance should not change. Okay. So definitely what should happen now? Q should be remaining same, means C should remain same. Q is equal to 1 by omega CR na. Q is not changing, means C is also not. So C should be same. The total C should be 300 picofarads. Then automatically X will be equal to 100. Right answer for is 100 picofarad. The simple question is mat karna. Okay. Let us go for the next question. Number 2. The Q meter works on the principle of dash. Fundamentally, Q meter works on what principle? It works on the parallel or series resonance, because our RSH, L RLC. Friends, okay. So these are some questions on meter. And actually, after electronic measurements, the Q meter parameters are more important. Okay, can be used for the self-inductance measurement, and also useful for the capacitance measurement, distributed capacitance. So parameters measured by Q meter parameters or what are the parameters measured? Self-inductance of the coil, factor of the coil, resonant frequency of circuit, capacitance of the coil, effective resistance of the coil, okay. These all are the measures. Q meter. Okay. So before closing the topic, the total electrical and electronic measurements, important topics we have discussed. Under the electrical measurements, we have studied the bridges. Under the bridges, we have seen the AC bridges, DC bridges, then measuring instrument. Okay. So plan effectively. Try to complete these topics first, whatever that I have given in a one shot series. So try to complete these topics in series first. Then you try for the other chapter. Most important topics we have discussed here. Okay. So in a single stretch, if I want to tell you the topics are explained, measurements, especially the measurements, total measurements can be in two ways: electrical measurement, electronic measurement. Try to segregate and first complete the electrical measurements. In the electrical, you try to complete error analysis first. After the error analysis, go for the measuring instrument. Under the measuring instruments, DVMs, pig iron, dynamometer, electrostatic voltmeter, the miscellaneous instruments like instrument transformers and thermal instruments. And after that, you please go through the power measurement and energy measurement. Power measurement. Under electronic measurements, majorly you can get the questions from turbo, that's meter, and for EC. So these are the major topics. Try to complete all these topics first. And you can follow my YouTube crash course also on the YouTube channel we are starting. And whatever the content we have not yet covered in this, that will be possible on the YouTube crash course. So try to forward these sessions for as many as people as possible. And in YouTube crash course, I will be discussing more questions. Here I have discussed majorly about the working principle and operation of the instrument, but there majorly I will be talking about numerical problems. So in that session, I will be explaining the maximum of numerical problems on all the topics, all those things. And whenever you are planning, please follow a matrix. So that is what we call as priority matrix. In that priority matrix, you keep most urgent and most important, most urgent and most important, most urgent but not important, right? Not urgent, low urgent, low important. Like that, you segregate the topics. You know? So try to speed up your preparation. I don't want to waste your time. Enough number of objective questions. Please take those objective questions, practice, and try to solve more. Thank you. We'll meet in the YouTube class.